Okay. Yep. All right. Hello. My name is Eigil, as was just said, and I'm a PhD student. I defend my thesis next month, and I've been working on this stuff, which is like modeling. Long term can mean different things, but in my context, it means modeling from the Little Ice Age, which is the end of the 1800s to today. And I've specifically focused on this glacier, which is in East Greenland. I'll show you a map in a second. I'll talk a little bit about sorry, I'll just do the overview. So I'll give you a bit of background first of this idea and what I've been working on, some of the modeling basics within the field. Then I'll just discuss the baseline model that I developed, and then how it can kind of, I think it serves as a good kind of small example of why it's nice to move to Julia. And yes, so basically it's going to be a small like case study of using Julia to take advantage of auto differentiation to solve some physical modeling issues. All right, so the interest area is shown on your right, so that's Eastern Greenland, and it shows the whole basin of this Pacific glacier. It's one of the glaciers that are kind of pretty important in terms of the total discharge, at least in the last 20 or 30 years. It has been a big contributor to sea level rise, which is also the kind of reason why ice modeling is interesting. And particularly I've been looking into how to model and reconstruct this glacier in the past 100 years approximately, since the end of the Little Ice Age. And that's interesting because a lot of modeling studies are mainly looking at the past few decades. And since we're interested often in 100 years projections, some of the dynamics and interesting dynamics of modeling are like kind of, it's hard to really investigate and understand what's going on a longer time scale when we base the models on a short, like when we parameterize the models based on a shorter time scale, basically. So that's the idea. Yep. So the reason why it's possible to do this is actually because these guys, they flew around over Greenland in the beginning of the last century. So around in the 1930s, they flew around and took pictures. The guy in the middle, Lauge Koch, was responsible for these missions, and he was a geologist and was interested in rock formations and stuff like that. There was also like a dispute with Norway at the time, who was settling kind of illegally in Greenland. And so they were also monitoring a little bit that nobody was living there without permission. Oh, but anyways, these pictures are then enabling us to get information about the past geometry of the ice. So let's see if I can use my mouse. Yeah, I don't know if you can see it, but this orange arrow is pointing to the so-called trim lines, which are lines you can still see in present-day imagery. So this is an image from 2013, and this is from 1933. And you can see the ice has thinned out, and this gives us some information about the thickness of the glacier back then. This is a glacier called Fenris Glacier. And also we get some information about how much the glacier has retreated based on this front migration data. So this information can kind of help us get an initial state for the geometry of the ice. Also, to those of you who doesn't know already, ice can be modeled as a fluid, and you can kind of get hints of why this is the case, because you can already see here in these black lines that it looks like kind of it's flowing. And so on longer time scales, like decades and so on, and even longer, it kind of behaves like a fluid. And this is some kind of small, I just took all the Landsat imagery from the 80s going forward. They're not geocoded correctly in the first part, but they'll stabilize around the end of the 80s. But I just wanted to, it's just because you'll get like the feeling of this flowing ice. Once it stabilizes a bit, it's easy to see. So now you can start to see that it's really flowing kind of into the ocean. So just to give you an idea of what's so up here is basically the ice sheet and the interior of Greenland, the ice sheet, and then out here is the ocean, and the ice is flowing out like this. Yes. All right. So some basics for the modeling. Basically, we take the Navier-Stokes equations and then we neglect momentum advection and inertia, and based on something called the power law relation, a power law relation called the Glen's flow law, we can then connect stress to strain, and that enables us basically. That's kind of the very rough outlines for ice modeling. More schematically, what is going on is that when snow accumulates and with time becomes like ice, then if you get enough mass, basically, it will start flowing under its own gravity, and it will flow, roughly speaking, like this. So it will flow from the middle and out to the edges due to deformation from gravity. And you can both have land terminating glaciers, as you see in mountains and also some places in Greenland, and then these ocean terminating ones. I've mainly been working with the ocean terminating glaciers since they're pretty interesting. They're much more dynamic, and they're both influenced by the ocean as well as the atmosphere and what's going on under the ice sheet. And here's the stress balance equations for the ice in its full form. So in order to model, we would like to reduce them a little bit to make it a little bit more easy. And we do so by this so-called shallow shelf approximation, which is where you kind of only consider the horizontal stresses. So you treat it as a kind of membrane. So all of this is considering the stresses on a like infinitesimal ice cube inside the ice. And since the glacier is much wider than it's deep, then you can kind of ignore, the idea is you can ignore the vertical components, and you end up with these equations. They are now reduced from this to this. And you can use if we use the last equation in the z direction, we can solve for p and insert it into the other equations. And so we end up with only two equations. And that's the shallow shelf approximation. And we can kind of image it as a kind of giant membrane that we pull or stretch, or like a sheet of paper or like a sheet of something. Yeah. So that's pretty common to use this approximation in ice modeling, especially if we do larger scale modeling, because it's computational a little bit more manageable. All right. Yes. Okay, so the next thing is that, so here's another schematic of an ice shelf, of a glacier. And the glacier consists, when it's like ocean terminating, it sometimes have this ice shelf, which is basically that the ice separates from the bedrock, and then it becomes floating. And the ice moves out this way, and then it breaks off and can become icebergs. And we have this kind of some of the interesting kind of points of interest is the grounding line, like where this separation happens. That's a very active point of research. And there's also a lot of research going into when the ice will break off. So like what's happening at the ice front. And then we have like the major forcing close to the ice front would be the ocean currents. Yes, so that's what this schematic shows. But the thing is that in the shallow shelf approximation, we actually assumed that we were working only with an ice shelf. But often ice is grounded, meaning it actually has some kind of friction with the bedrock. There's something opposing the flow, which would not be the case if it was floating. Additionally, it turns out that if we only model the ice with deformation only, then we can actually not reproduce the observed velocities. So somebody came up with the idea of introducing a proxy term, or like an ad hoc friction term. So you introduce this basal stress term that can modify the equations basically, and it's often modeled like this. So it's some coefficient that's dependent on the basal velocities. All right, so the reason why I've told you all this is because this term is, first of all, pretty important in modeling, and secondly, and we don't really, there's a lot of active research going on figuring out how to do this better, and it plays a big role in future projections. So some of the overview of what I've been working with, but also the idea behind, I'm going to show you some Julia work in the end. But basically, we use this shallow shelf approximation, and then we model it with the final element model software that's called the iSheet Sea Level System Model. It's pretty well known within the field and has been developed in 2010. It's a C++ program that is operated either through MATLAB or Python usually, and it has different capabilities. One of them is that they implemented inverse problems to calibrate some of these parameters inherent in the program, which is pretty useful. Based on surface velocities, you can then calibrate the friction so it matches what we observe. It also has this capability of adapting the element size to the observed velocities. And then there are several different friction laws implemented, and these friction laws there are a lot of different ones. This is actually not the most realistic one, but it's pretty easy to get it to work for examples. And also in my work, it turned out to be the most stable one in terms of actually doing some modeling. It consists, so this is the basal stress, and this coefficient is what you would invert for. It's just a coefficient. This is the effective stress at the bottom of the glacier, and then you have the basal velocities and some exponents. So in my work, what I had to do was I wanted to reconstruct the model, and in order to set up the model, you need to have initial conditions. So we got the geometry from the images I showed you earlier, but we still need the basal friction or the conditions underneath the ice. In order to do that, I solved the inverse problem for present-day data, because to present-day data we have surface velocities. You can see down here is a velocity magnitude map of Kangerlussuaq Glacier, and you can see it goes from almost zero, and within how much is that? Within 50 kilometers, it increases to be around 10,000 meters per year. So it's a quite huge change in the magnitude scale. But then we can invert for friction coefficient in this based on these velocities, and then since I don't have velocities in 1933, then we assume that it's constant and that this friction coefficient doesn't change over time, and then we can use the geometries to initialize the model, run it forward in time based on surface mass balance models. So these are atmospheric forcings, and then changes in the front position. So this is also some kind of forcing. It's just where the front is, basically. We can compute the misfit and then use that to either inform updates of this process or to inform just the misfit in general, which I also did in the paper that I released on this work. So one of the huge issues with this work, or what I really struggled a lot with to get to work, was that since I have no observed velocities, as I just mentioned, I cannot invert for friction coefficient in the past. At least not in a kind of not in the methods I had available at the time. But I still had to take care of this area of the domain, which is now ocean, but it used to be ice covered. So basically I don't have any friction here, but I need some friction for the model to work. What I did was basically this is an extrapolation problem, and I need to figure out how to solve this somehow. So first, it might seem like it's like a small area compared to the total area, and might not be that difficult. But since there's no ice immediately around it, and because of the structure of the flow, and since all the ice for the past 100 years has to pass over this area, this friction in this area is super, super important, and it's very sensitive to what happens here. So what I ended up doing was I did like a correlation based extrapolation where I correlated the bedrock topography to this friction coefficient in the known area, and then I used that to extrapolate. And by tuning it a little bit, I got it to sort of work, having both realistic initial velocities, but also not having like a major ice mass build up over time. So it was like a trade-off between having like a plug in the end or like having a very big slide. So neither is very nice because they're not producing results, present-day results that are realistic. But it was pretty annoying. You know, this process was not so satisfactory from my own point of view. You know, it's a lot of tuning and it doesn't, like it worked and it has like the misfit, present-day misfit was acceptable, but it was not like the best. And here you can see the actual friction coefficient field that I've extrapolated. And you can see it's kind of, you would say, some kind of average with this small bedrock signal in the middle. It's slightly darker. I don't know if you can see it, but it's slightly darker in the middle. And yeah, it kind of worked. But this process, especially if this was to be more generalizable and repeated for other glaciers, it would be very interesting to figure out a better way to do this. And this kind of is bringing me to automatic differentiation in a second. So I just wanted to mention that I tried various different of these friction laws, and the one I ended up using was the only one that worked. It involved a lot of tuning, and I also tried these spinning up methods and trying to correct the initial geometry and stuff. I tried a lot of stuff to make it work. So yes, so now we'll go to the Julia part. So it's pretty. So this work is mainly done by so far by Cheng Gong and Matthew Mogliam at Dartmouth College. They have been working on porting the original source code to Julia, but it also means that it has like a C++ or MATLAB like syntax still. It's pretty one-to-one. I think so. As far as I know, so I was, I wanted to present this here, but it's mainly their work, and I think the reason for this was to ease the transition from existing users of ISSM, since it's quite there's a lot of users of this software, and also to make sure that things are working like for the right reasons. Yes, so it's still pretty early stage. So we've managed to get stress balance solving to work, what I showed you in the beginning, and then also running transient solutions, so running the model in time. It uses Enzyme for the automatic differentiation, and then I will just now go through two simple tutorials that I also uploaded on the JuliaEO site. Here we are. So if you're interested, maybe I should zoom in a little bit. So a bit more. So if you're interested, it's and you want to install the package, it's at the registry. Just at the moment, there's apparently a bug. I think they're waiting to get fixed in Enzyme. So you need to add the hashtag main to get the main channel from the registry. Otherwise, it won't work. Right. So we can import it. I think I'm just going to talk through it because running it will not provide so much more information. And this is the main object in the program. It's a model object, and it has all of these properties like a mesh and a geometry, ice geometry, and mask, blah 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 blah. And all of these can then be updated and set to something specific. Initially, so this first tutorial is just creating a square ice shelf. It's pretty basic, but gives a nice idea of what we need as a minimum requirement to actually model the ice with the final element solver. So we set up a final element mesh using this triangle method, which takes in a model object and then the domain name and the resolution you want. So you can see you input like these EXP files, which in this case is just some square with some size, and you give the resolution of 50 kilometers. And then you have the set mask function, which will inform where you have floating and where you have grounded ice. And it has this keyword called all that just sets everything to floating So it gives you this mesh, which has where all the nodes are floating. And then we can start setting up the geometry of the ice, and we define the thickness to be just a function of y, having like a max and a minimum thickness. Boom, boom, and we get like this. So if we go back, so it will be its thickest down in this end and it's thinner out in this end. And it kind of resembles, that's just to show you why it sort of makes sense. So you can see it kind of resembles the outer part, the floating part of an ice shelf, where it's thicker in the beginning and it gets thinner as we get closer to the ice front or the Earth's ice terminus. Additionally, we can also we have to define the base. So that's the base of the glacier, what's underneath it, and we do it based on the hydrostatic equilibrium. So it looks like this, and we get then the result looks like this. And again, it's kind of resembling this schematic. You have like more submerged ice when it gets thicker, and when you get further to the thinner part, it's less. So yeah, it looks like that. And then finally, you can define the ice surface as by just adding them together. Then we want to make sure that the bedrock, so this is the bedrock, that it's not touching the base. So we subtract some meters basically. And then we'll start up setting the initial conditions and the boundary conditions in a second. Yeah. So the initial conditions are we're just gonna set the velocities to 0 in both directions. And then there's a small recap of what I already told you. So this is the shelf stream approximations, or the shallow shelf approximations in tensor form. And here you have the tensor expression, or the tensor written out. And then we have this Glen's flow law that I actually didn't include in my slides. It's written out like this, where we have some exponent and this prefactor, which is determined experimentally. So it's usually just set to some constant that you can find in some tables. It's temperature dependent, and it's set here. So we set those two things up, like the exponent and the prefactor. And then we have we use this Butt's friction law that I told you about before. We set P and Q to 1, and the rest is already given. And here the friction coefficient actually doesn't matter. I think it's more the code doesn't ignore this thing, despite the fact that all the nodes are floating. So there is actually no effective friction in this context, in this example, but there will be in the next one. Then finally, we have to set the boundary conditions, and we do so by saying that the top of the domain is the calving front or the ice front. So that will have like Neumann conditions, and then the surroundings will have Dirichlet conditions, and that's what we set up here. So we find these vertices that are on the top boundary, and then after that we set the Dirichlet conditions by doing the same thing essentially. So this SPC is the velocity on the boundaries basically. Then we set some numerical tolerances, and then we can solve the model using the solve function, and we tell it to solve the stress balance. It runs for a while, and then we can then plot the velocity solutions. So this is the velocity of this kind of theoretical ice shelf, where we can see that closer to the thick part of the glacier, or the ice shelf, sorry, it's slower, and then it speeds up as we go towards the terminus. Yep, and then I will just go through this other example where we try to use some AD to investigate the sensitivity of the model basically. So there's some imports, and then instead of setting up all the geometry stuff and all that again, we import a model from one of the MATLAB versions that is already, like, this model has already been set up with all the geometry. It just saves us some time. It complains a little bit because there's some additional things that hasn't been implemented yet, which I implemented in the original, which I implemented in the ISSM version, the MATLAB version. And then we can look at the friction field. So this is the friction coefficient that results from doing an inversion in a real life setting. So it has like higher friction in these areas where the ice is kind of not moving. Maybe I should just show you this. And this is the resulting velocity. This is the observed velocities actually. So you have, this is the Pine Island Glacier in Antarctica. It's a quite important glacier, and it has like a pretty big floating part here in the end, and then it becomes grounded around here. And when you use the observed velocities to infer the friction coefficient, you get something that looks like this. The resolution is a bit coarse, which I think is just to speed up this tutorial, basically. It could be much finer. Yes, then we solve the forward model to get modeled velocities. And it's just equivalent to what we just did before we saw in the square ice shelf case. And then we can plot that. It looks like this. So it's slightly different than the observed, but it's kind of close enough. And then we get to the sensitivity analysis. And here we use enzyme, and then we've defined like the cost function like this. But instead of using observed velocities, which could also be interesting, in this tutorial we just set it to 0 to investigate where the modeled velocities are most sensitive to the friction coefficient, basically. So we're interested in this gradient dJDC, which is the gradient of the cost function with respect to the friction coefficient. So we'll get some idea about where the friction coefficient will mean most for the modeled velocities. Yes, and I think we'll hear more about this 80 stuff tomorrow if some of you don't know what it is, but basically we can then propagate the gradient back to the input and see how sensitive different input parameters are, like the output is to the input, basically, and use it for many other interesting things. So this is defined like this. We tell it what the independent variable is, and then because of this legacy one-to-one porting, there is also some you need to support, give it kind of information about you give like some string keywords about what you're interested in. So in this case, the friction coefficient, and that you use this specific cost function. And then we solve it. And this time it's because we've set this is control to 1, it knows that it has to solve like the inverse problem or the 80 problem. Solve it as with automatic differentiation. And when it's finished running, we can then look at the gradient. So this is the JDC. And so to me, I thought it was an interesting small comment or like confirmation about what I found in a lot of my own work that took a long time, was basically that the model is really sensitive. Like the friction coefficient choice really affects the modeled velocity a lot, very close to this grounding line and close to the front in the main trunk of the glacier. So you can see this is kind of where the transition is if we do like a simple approximation of the grounding line. So that's really where the friction coefficient plays the largest role, which is kind of just emphasizing the point that the reason like this area is just super important, and it's important to increase our understanding of the friction in these areas. Yes, so far we can also repeat this work for the rheology, this B parameter, to kind of figure out where it's most sensitive. And we could also set up the problem differently and try to estimate or update the friction estimates that we already have based on observations. What I hope to do myself next is, first of all, I would like to start contributing more to this package, first of all. And secondly, let me just go down. I have this, I wanted to try and experiment with introducing, instead of using these friction laws, then instead like proposing a model that can give you the basal stress directly. And to do that, I was thinking to use some kind of neural network in this physics-informed setup. And the nice thing is that now I can use the ice model from dJUICE, and I can differentiate it, so I can actually get the gradients to update a like hypothetical basal stress model that would be able to infer some basal stress instead of using known or like these friction laws. It would be very interesting, I think. So that is all for me. Yes, thank you. Yes, Alex.
Super impressive.
Thanks.
How difficult was it to implement enzyme? Like, did you have to structure your code in a friendly way that enzyme was able to interpret, or is it fully automated? Doesn't matter what you throw at it.
So I was a little bit on the side during this process because I was finishing up my PhD, but I know from Chengong that they had some troubles actually because they wanted to use the analytical adjoint that they already knew. They wanted to use that instead of getting it from enzyme, and that was actually a bit tricky. It took some time for that to work out, but I worked closely with one of the guys from the enzyme team to make it work. So it took a bit of effort, I think, as far as I understand. Yeah. Is that? Yeah. Yeah. But I'll talk to him after this actually, so I can ask for some more details and come back to you. Yeah. Yeah, it's a good question. To me, I think it seems like a bit of an aside from my point of view. As you know, they're interested, but I think they still need to prove that it has enough. How can you say, like, it will benefit them so much that because you know there's always a challenge of being able to answer interesting research questions in order to qualify, actually spending a lot of time on working on it. And since a lot of ice modeling is kind of only 10 years old, like numerical ice modeling, there's still a lot of interesting questions to answer with normal numerical ice modeling, is, you know, the stuff that's already working. So, but my own hope is that they will spend more time. I think they're also interested. I mean, the community is super great, right? And the language is amazing. So it's something at least I would also like to push. So. But yeah. 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 Yes, and also I think so. Actually, there's been a little bit more. It has had a bit more momentum for the past half a year, but I think when they started out, they really quickly hit this roadblock with the enzyme stuff. So, but now they managed to get over it, and it's going a bit quicker now. Yeah. Cool. Thanks. That's it, I think.